So in the course of integrating rational functions, it's going to turn out that some of the decompositions that we will get will be of the form 1 over x squared plus some constant b, or x over x squared plus a constant b. So it's kind of useful just to know in the general form what these antiderivatives are. So let me just show you how to work those out, and then we'll be able to use them without having to do them in line. So if I find the integral of x squared plus b, of 1 over x squared plus b, like that, the thing to recognize about this is that you can do it by use substitution, but not sort of in the easy way. This is going to look very much like it looks very much like the derivative of arctangent, and that's not a coincidence. So let me show you how to do that. What we're going to do is we're going to pull out a factor of b. So I'm going to write 1 over b. This is the antiderivative now of 1 over b times x squared over b plus 1. You can multiply that out and verify that those are in fact equivalent. So just be clear what I'm writing here. That's x squared over b plus 1 in the denominator. So now let's just put it in a little bit more of a usable form. This is going to be the antiderivative of x over the square root of b squared plus 1. Now what I can do is I can set u equal to x over root b, and du equals 1 over root b dx. So that gives me root b du is equal to dx. So now what I can do is I can replace everything just the way it looks in the integrand. So I have 1 over b times dx is equal to root b du. So that's root b du in the numerator. And in the denominator we have x over root b is u. So I have x over root b squared, which gives me u squared plus 1. This is just equal to root b over b times the integral of du over u squared plus 1, which is root b over b is just 1 over root b, times, and this antiderivative is arctangent of u, which equals 1 over root b times arctan of u is x over root b, so x over root b plus c. So that's the antiderivative of expressions that look like this over here, this 1 over x squared plus b. Now let's do the other one, which is actually a little bit simpler. Let's find the integral of x dx over x squared plus b. This can be done by a more straightforward sort of use substitution, so that's just going to be u equals x squared plus b, du equals 2x dx, so x dx equals 1/2 du. That gives us here that this is equal to the integral of 1/2 du over u, and we know that that's just going to be this is just going to be 1 over 2 ln of u, which is 1/2 ln of x squared plus b, and then we can say plus c. So here are two antiderivatives that are going to turn out to be fairly useful as we go ahead and find integrals of rational functions. I'm now going to turn to an example where we actually make use of both of these. So what we have here is the problem to evaluate the integral of 4x squared plus 7x plus 7 over x plus 1 x squared plus 3. What we can see here is that we have a linear factor and a quadratic factor. Most importantly, this quadratic factor is irreducible. If, let's suppose, the factor had been x squared, let's suppose it had been something like x squared minus 9, we could have simply factored it as x plus 3, x minus 3, turning it into two linear factors. The important point here is that there's no way to factor x squared plus 3 using the real numbers, so therefore we have to treat it differently. So what we want to do is recall that the rule for a quadratic factor, for an irreducible quadratic factor, is that instead of getting just a single constant, it gets two constants and an x over it. So let me set this up. We have a over x plus 1. I'll deal with the linear factor that way. But for the quadratic factor, we have to put bx plus c over it. And there we go. So this is the correct decomposition setup of this problem, of this rational function. So I'm going to write x plus 1, x squared plus 3, like that. And there we go. So that's the decomposition. What I'm going to do is I'm now going to multiply through by the denominator, just as I've done in the past. That gives me x squared plus ax squared plus 3 plus bx plus c x plus 1 is equal to 4x squared plus 7x plus 7. I'm now going to try to zero out one of these. I can zero out this whole term here in order to solve for a just by letting x equal negative 1. So that's going to give me a times negative 1 squared is 1 and 3 is 4. And then this whole thing here, negative 1 plus 1 is 0, so this just becomes a 0. And now this becomes 4 times negative 1 is 4. 7 times negative 1 is negative 7, and then plus 7, so that equals 4. So what I have is a times 4 equals 4, which clearly gives me a equals 1. So there, I have one of the constants already. Now, the problem is that I can't actually zero this constant. There's nothing I can set x to that's going to make x squared be negative 3. So there's no way to do this by that technique. So what I'm going to have to do is the thing where I group the constants together. We already know that a equals 1, so I can simply replace a with 1. This is going to be x squared plus 3. In other words, I just let a be 1 and I'm just multiplying that out. 1 times x squared plus 3. Now I'm going to multiply out this whole term, which I have to do using, oh, they call it in high school the FOIL method. I've never liked that acronym, but if you want to call it that, that's fine. So we have bx squared plus bx plus cx plus c. By the way, the reason I don't like acronyms is that acronyms are sort of a thinking substitute, and I like actual thinking, not memory tricks. So anyway, so let's group together the x squared and x in constant terms. So this is going to be x squared. We have here x squared 1 plus b, so that's going to be 1 plus b. And now let's group the x terms. We see that the coefficients of x are b and c, so we can put a b and c there. And then finally, the constant terms are just c and 3, so that's going to be c plus 3, and this equals 4x squared plus 7x plus 7. All right, well, it should be fairly easy to solve for b because we know that the coefficient of x squared is 4, which means that 1 plus b is going to have to equal that coefficient, or 4. So that gives us b equals 3. And we also know that the constant term is 7, which means that c plus 3 is equal to 7, which means that c has to equal 4. So what this means, actually, is that the original integral, let's do it over here, the original integral is equal to the integral of 1 over x plus 1 plus bx plus c, that's going to be 3x plus 4 over x squared plus 3 dx. Okay, so it's going to turn out this is a little easier to do if I just break this up this way. So this is going to be the integral of dx over x plus 1 plus, I want to break up this whole expression here. This is going to be the integral of 3x dx over x squared plus 3. And then we'll put the constant part, that's going to be 4 dx over x squared plus 3. Now why did I do that? Look at this and look at this. If I go back here, I already found what the antiderivatives of that function and that function are, so I'm going to be able to use those if I break it up, if I break up the fraction in this way. So this is simply going to equal ln of x plus 1, and then this is going to be, we have x over x squared plus 3. The antiderivative of that is x over x squared plus b. Its antiderivative is 1/2 ln x squared plus b. So that gives us, since we have a factor of 3 there that I have to deal with, I'm just going to multiply that result by 3. So that's 3n ln of x squared plus 3. And then finally here, the antiderivative of 1 over x squared plus 3 is going to be 1 over square root of 3 arctangent of x over square root of 3. So that gives us here, since we have a factor of 4, I can multiply that in. So that's going to be 4 over root 3 arctan of x over root 3. And then, of course, the hardest part of the problem is the plus c. And that's the antiderivative of that relatively everyday straightforward rational function. So, and by the way, there's one other tweak I want to put in here. notice that x squared plus 3 can never be negative, so you don't really need these absolute values in here. We can put it in parentheses like that. It's not really wrong to leave in the absolute values, but don't tune out and say therefore you don't have to do it, because as you know, I want you to stick the landing every time. This just looks bad. It's like doing that perfect vault and then falling down at the end if you leave the absolute value in. It's not necessary. The cleaner solution takes it out and looks like I've written here. So there's the answer.